On behalf of the Department of Computer Application, under the aegis of Human Resource Development Center, Integral University, I, Farhazia, Assistant Professor, extend a warm welcome to all participants to the 2 weeks blended faculty development program on the transformative learning through interdisciplinary artificial intelligence and machine learning application in emerging domains. We are honored to have with us today Dr. Sunakshi Mehra, who is currently serving as an assistant professor in Department of Computer Science and Engineering at Delhi Technological University, Delhi. Dr. Mehra possesses an excellent academic background. She completed her BTech in IT from Indira Gandhi Delhi Technical University for women, followed by MTech in IT from Guru Gobind Singh Indraprastha University and earned her PhD in IT from Delhi Technological University with specialization in speech recognition and natural language processing. We welcome you, ma'am. She has extensive teaching and research experience and has previously served as faculty member at Guru Gobind Singh Indraprastha University and Galgotia College of Engineering and Technology. Dr. Mehra's research interest encompasses artificial intelligence, machine learning, deep learning, speech recognition, natural language processing, computer vision, signal processing, linguistic, and phonetics. She has made significant scholarly contribution with more than 9 publications in reputed international journals, including 8 papers published in SCIE Index Journal, in addition to conference publication, book chapters, and patent. She also served as reviewer for several reputed national and international journals and conferences. In recognition of her impactful contributions, Dr. Mehra has been conferred the Commendable Research Excellence Award by Delhi Technological University. With her strong interdisciplinary expertise and research acumen, we are confident that today's session will be highly insightful and academically enriching for all the participants. I now respectfully invite Dr. Sunakshi Mehra to commence the session. Thank you, ma'am.
Thank you so much for a lovely introduction. So let me, I'm very honored to be a part of the Integral University or part of this faculty development program. Thank you so much for the invitation. Uh, Thank you so much.
We are, thank you.
The topic for my presentations is AI-driven multimodal fusion for speech recognition. So starting from the very beginning. So basically the speech recognition, so before starting the actual, say the artificial intelligence or the fusion technologies, we must first be aware of what exactly the terminologies that and the properties they hold. So the say speech recognition, it is a cornerstone of the modern artificial intelligence, and it also bridges the gap between the human communication and the say machine processing. So we can say that whatever we say, it is a being can be say the identified by using the speech recognitions, since it is also the cornerstones and the modern artificial intelligence are using the speech recognitions. It also bridges the gap between the human and the machine. So these speech recognitions, by translating the spoken language into the actionable data, so by translating we can say the spoken language to the text to the commands, that all can be our actionable data. So it powers everything from the intuitive voice assistants to the sophisticated automated transcription services. So as we have seen in our day to day life, we have these various voice assistants like say the Amazon, say the Apple's Siri, we have the say the Microsoft Cortanas. All these are the voice assistants that can be used say to identify or to say deal with that query. So that is being said as the input as a speech. So the say the language that is being used for the speech recognitions, it is the Python programming language that we mostly used to build our speech recognition model. So since the Python, it has the various say the libraries and the predefined say the features or the predefined libraries that can be used to analyze the acoustic properties that the speech holds. So it is one of the say the programming languages that is mostly opted for the speech recognitions. Also we have the other tools like the MATLAB can also be used, but I will highly recommend that we must be aware of the Python programming, since it is the say the basics of say of bridging the gap between the speech and the say the machine. We can build our model by using the Python programming languages, since it holds a various say the properties that can be say really help to make our speech recognition model. Now, so before coming to the say directly to what exactly we are going to head lead to the first we will see what exactly how we can differentiate the two terminologies like the voice recognitions and the speech recognitions, since they sound very similar to each other. So first coming to the speech recognition, so as we have already seen that the speech recognition is about understanding what is being said. So it is not say depending on the say the speaker, it is only say important to identify what is being said by the speaker. So it converts the spoken text or spoken words to the text and the command. So it so whatever being said by the speaker, we are not aware who the speaker is, but we only focusing what is being said or what is the content of the speeches we have. So the main goals is to recognize the content of the speech, not who is speaking. So it is commonly used in applications like the transcriptions tools, voice assistants, such as the Siri or the Google Assistants I have already discussed earlier. So it has the one of the applications in generating the transcriptions. Also, these speech recognitions we also use in our day-to-day life. Now coming to the voice recognitions, well, the other name for the voice recognitions is a speaker identifications. So that is a totally different from the speech recognition. So voice recognition focuses only on identifying who is speaking. So it analyzes a person's unique voice features to verify their identity and does not focus on converting the speech to the text. So the speech recognition's task was to convert the speech to text. However, the voice recognition task is to identify who is speaking. So it is a mainly used for the say the security purposes for the authentications. So now we also have the voice based login systems which greatly help for the say security. Also we have this say voice login systems in our mobile phones as well. To unlock our devices we also have this functionality now. So the success stories that leads to the say the ASR is the deep learnings is the say the main tool that is the helps to say the to actually say generate a very say helpful automatic speech recognition model. So at this case, you can see first I have seen that the speaker is saying something, and that is a say it is generating the transcription. So basically, that is our ASR model that generates the text transcript. Now at this slide, you can also see I have shown various the audio waveforms. So these are the say the representations of the speech we have. Now also we can also have these say the mel spectrograms, which is one of the say the speech features we have. uh, then also we have this mel frequency substral coefficients, that is also one of the representations for the speech. We will discuss each of these features in details in later stage. Also these say the speech features that is given as an input to the neural network. So at the input we have this say the speech or the audio samples that we have. Then we have the say the various hidden layers, and also learning through these hidden layers we will generate the output. Because so that was the say the simplest model that we have seen now. So basically as the speech, as we know, it is the main medium by which we the interactions between the humans takes place. The main aim of the speech recognitions is to translate the human speech into the spoken word. So we are translating the human speech to the spoken words that we that is are the main goal for the speech recognition. So it is one of the most challenging tasks due to every speakers has their own say way of speaking. So every speakers will have the say his speech intensity of saying certain words. So also also as a single speaker also we have these characteristics keeps on say differentiating or keeps on say distinguishing. So we can't rely totally on the say the speakers. However, the speakers attributes also plays a major role, since to identify the speech, also since the intensity or the pitch or the amplitude the speech holds may vary person to person, so also within the person also. So it is one of the most challenging tasks due to the speaker's attributes, style, and accent. Now, in the era of technology where automatic speech recognition plays a vital role, so most of the technologies are processed by the supervised learning approach, which helps greatly in improving the services provided to customers related to voice. So, as living beings communicate through speech, which can be analyzed to identify words and tenses by recognizing the flow of utterances. So, the flow of the utterances or the flow of the spoken contents leads to the words and sentences. Now, due to the rapid development in a speech processing, using supervised learning always plays an say the instant or the important role in improving the communications. However, we also have these background noise which always have a huge impact on the speech recognition process. So mostly for say the removing the backgrounds, we also have the various speech filtering techniques, which we will discuss later on. So these are greatly helps us to remove the background that we have in the speech. So the detection rate in the presence of the background noises is still unsatisfactory. So we currently facing this issue, and it is also say that one of the say the leading future techniques that need to say rely on, since we have this background noise or the ambient noise which need to be removed so that the say the speech can be identified with the greater accuracy. So the importance we have the see recent advancements that we have in a speech recognition. So basically, the recent advancement in speech recognition have significantly improved how humans interact with the machines. The integration of the natural language processing enables systems to understand content, the intent, the context, and the meaning. Okay, so natural language processing really helps us to actually find the meaning or the intent or the say the for examples we have certain sentence that is also the sarcastic, so we also say with the help of the natural language processings we are able to identify the sarcasm also in the say the speech. So this makes the interactions more like a natural and the accurate. The rise of the various voice assistants and the smart speakers have made the say speech recognitions are part of the our everyday life, allowing users to perform the tasks hands free, improving accessibilities and the convenience. So we have also say the various advancement in the deep learning techniques. So previously in the speech recognitions we have the various say models like the hidden markov models or the Gaussian mixture models. Now due to the advancements we have the deep learning techniques, natural language processings that greatly help to enhance the recognition accuracy. Also the noisy environment for say the different say accents can also say be the recognitions in that case also is being improved now by deep learning techniques. So this has expanded the reliability of speech based systems in the real world applications. Now support for the multiple languages. Since we want to, let's suppose we want to identify the language like a Tamil or the Arabic, so that multiple languages can also be say the case that where the speech recognition plays a major role, since it is a more inclusive or globally accessible, enabling the communications across the diverse linguistic communities. Now finally we have these the real time transcription services, which has transformed the areas such as the education, the healthcare sector, the meetings. So for providing like an instant or a accurate speech to text conversions, improving the productivity as well as accessibility for all the users. Now, so before the deep learning era, for the speech recognition models, we have this hidden Markov model, Gaussian mixture model. Say are the two must learn technology for speech recognitions, and now there are the say the hybrid systems which also have the say we have the hybrid fusions of the hidden Markov model, deep learning model. So we can make our the models that will be say the will have the better recognition accuracy. So we have more design choices now. However, we previously we didn't have the much say the choices. However, for many generative models, the hidden markup models remains the important. So whenever we want generate the query, or whenever we want like the input to be the speech, and also to the output should be like a text or a say the answer to the query. So in that, the hidden Markov models plays a major role. So now starting with the speech recognition model. So what are the say the what are the attributes that the we can use so that we can train our model, make our model best in recognition. So these are the few terminologies we should know, like the acoustic, lexicon, and the language models. So speech recognitions can be viewed as a finding the best sequences of the words according to the acoustic, the pronunciation, lexicon, and the language model. So over here you can see we have this audio. This is our audio, which is our input. Now these input is a change to the spectrograms which I have shown you earlier. So this is one of the representations of the audio we have. And also it is a say the more closer to the human perceptions, or as the humans speak. So it has the say it actually the holds the human auditory properties. So now this say also we have this spectrograms. It can also have the like the 39 features. Now these features are extracted from this audio waveform. Now also you can see we have this acoustic models where actually may the say the utterance being said is being modeled. Now also we have this lexicon. So now since at this case you can see we have the word, so we can break these words into the we can say to the phonemes that is represented over here. So we will also see what exactly the phonemes are. Now at this case you can see also we have these language models. In the language models, from the say the present word, we are looking at the previous word. So with the help of the word pairs we can also say processing. So you can see all these say the acoustic model or the language models is used to identify what is being said. Corresponding to that, we also have the equation mentioned at this case. So you can see the acoustic models, it is represented by the px. So over here, whatever the say the acoustic features we have, and for the particular word we have to identify its the probability that will be our acoustic model. And then we have this language model. So this language models where we have the historic informations and the present informations that leads to the what exactly being said. Also you can see starting with the audio signals, it is divided into the short overlapping frames. So we have for this particular case we have taken the 25 milliseconds durations, and with each frames which is shifted by the 10 milliseconds. So for every frames we have the extracted the mfcc features to represent the acoustic characteristics. So the 39 values that we have seen over there, it was actually the mfcc features, that is the say the acoustic properties of the speech. Now, the main goal of the speech is to develop a statistical model so that can predict the most likely sequence of the words. For examples, we have the like a cat sits on the mat, so we will see how likely that these words relatable to each other, and how likely they can be, say the speech recognitions can be produced. So with the help of these informations, we can actually recognize the word. So one possible approach is to examine all the say the feasible word sequences up to a certain maximum length, and select the sequence that best matches the extracted acoustic features. So over here you can see the same say equations that I have shown you earlier. Over here we have the corresponding acoustic singles we will be having the word. So to identify this, we have applied the bias theorems that we have already studied or seen in our say in most of the technologies that we have. So now the that is the very basic probabilities say the bias theorems that is used. So by applying the bias theorems, you can see we have this particular equations. So for the particular say the acoustic vectors, that is our feature vectors, we have the for corresponding word whatever the say the mfcc features we have, that will lead towards our acoustic model. And from the say the previous informations and the present informations within the word, we can actually use the language models, that the both these informations on the probabilistic scores of these equations will lead to our the word sequence. Over here, you can see again the same things. We have this speech processings where we have these features. They are represented by the capital X, and with this capital X has the say the equations like starting from the say the 1 to the T. So that is at the duration of this particular say audio samples that we have seen that it is of the 25 milliseconds. Now it is being broken down. So in generalized, we have mentioned it in this way. Now at the acoustic models, so to handle the acoustic models, the approach that is being used is the Gaussian mixture models. And for the say the pronunciation models and the language models, for these two technologies, we basically use the hidden Markov model or the language model. So you can see for handling the acoustic properties, we use the Gaussian mixture model, and to handle the say what is being said, we use the hidden Markov model. So also in the previous slide, we have seen the phonetics. So what exactly the say the phonetics are? So basically, they are the say the place and the manner of the articulation or the say the human articulates. So it depends upon how the speeches are produced, and also it depends upon the position where the sound leads to. So over here we have the say the these are the say the manner of the articulation, and these are the places of the articulations. For examples, we have the bilabial, so that is the say the sound that is generated by pressing the lips together. So for the dental, we have the say the sound generated say the from the dental part. So these are the some the say the places or the positions where the sounds being generating. Also we have these plosives, which means if the sounds is say generated by stopping the airflow, or these we have whenever we have this hissing sounds that leads to are the fricatives. Also for example, the sounds that is generated from the nose makes are the nasal sounds. So these are the sums of the say the manner how the say the sound is generated. And the basically the this is the international phonetic alphabet that is being used whenever whenever we are dealing with the phonemes or the say the phonological properties of the sound. So we basically have this as standard which need to be used in this way. So in say the in the lexicons, we usually have the 44 this IPA, the international phonetic alphabets, that is being used for a particular say for generating the phonemes. So now, whenever we are dealing with the pronunciation model, so we have to always take care of the international phonetic alphabets, their standardizations. Always we have to follow these rules. So the pronunciation model maps the words to their corresponding phonemes, either using a say pronunciation tables or by relying on the corpus that is already phonemically transcribed. The acoustic model focuses on modeling the probability of a sequence of the acoustic feature vectors, which gives the sequence of the phonemes. So rather than the whole words. So as we have already seen that by using the phonemes, we can also analyze what is being said. So phonemes also plays a say the one of the important roles, since the well every individual has their own way of saying the words. Also the in the phonemes we also have the stress attributes. For example, say if we have the like a zero stress, which means the word is being spoken with no stress. And whenever we have the intensity value is a 1 to 2, so we will have the at the 1 we will have the little mild stress, and at the 2 we will have the severe stress. So it also depends how much the stress we are giving to any particular word. So that also leads towards the say the difference in the pronunciation. So also whenever we are building our speech models, we also have to take care of the pronunciations. We also these pronunciations models, if we take care of it, also it will lead to the better accuracy. So the one of the GitHub tools that we have for this is the author who has taken the letters and it has generated the phonemes. So for every particular language, for examples, we have the language to the Arabic, to say the Indian languages like a Tamil, also for the Vietnamese, Korean language, we can also generate the phonemes corresponding to that. So also this author has also given how he has generated from the grapheme, how he has generated the phonemes. So from the letters, how he has generated the phonemes by using the international phonetic alphabet that we have seen earlier. Now coming to the language model estimates how likely a sequence of the word is. So grammatically correct or meaningful sentences such as the I watch a movie are assigned the higher probabilities, and that are incorrect or unlikely sequences. So it helps us to identify what the most likely the word sequences, so that we can identify the word with the better accuracy. So it predicts the next word based on the previous information. So whenever we model, whenever we are using the language models, the Markov model or the Markov property plays a major role, since for the language modeling we use the hidden Markov model. So each word depends only on the intermediate preceding words, and these probabilities are typically estimated by counting the word pairs in the text corpus. So also you can see we have these text pairs where we take the present informations with the previous information. So by combining the acoustic model, the language models, we search for the text sequences and the the maximum likelihood for whatever the text sequence we have. So although this approach may seem indirect or computationally difficult, modeling the say for particular acoustic word to identifying the what is being said by using all these acoustic model or language models together, so it is leading to a very computationally difficult task. Now, the acoustic features of the each frame can be effectively modeled using the Gaussian mixture models. So basically, whenever we are using the acoustic modeling, as we have seen discussed earlier also, that for the acoustic modeling we use the Gaussian mixture models, and for the temporal transitions between the phonemes or the text, we use the hidden Markov model. So with an efficient search strategy, identifying the most likely phoneme sequence becomes feasible. So a hidden Markov model, it consists of the hidden states and the observable outputs. We will see now later on. Now the hidden states represents the phonemes, where the observable outputs corresponding to the extracted audio features. Now the transition between from one state to the another state, from one phoneme to the another phonemes, we will discuss. Now over here you can see in this particular slide we have this these phonemes that is generated for the sequences she just had a baby. So the phoneme sequence will be leading, also we have this acoustic property. So by having the the language modeling as well as the acoustic modeling, we are trying to identify the word or identifying what is being said. So, speech recognitions, the observable order is typically represented by the 39 MFCC features extracted from the each audio frame. The important advantage of using the hidden Markov based models, it is to avoid searching through the phoneme sequence one by one, which would otherwise result in exponential computational complexity. So hidden Markov models plays a the major role for decrementing the computational complexity. Also by applying the other approaches is like the Viterbi algorithms, we can also improve our the hidden Markov model techniques. Also the Viterbi algorithms are mostly used for the decoding technique. So whenever we want to decode some things, we use the Viterbi algorithms mostly in the text. So, in a typical automatic speech recognition system, the information from the lexicon, from the acoustic model, the language models, they are combined. Now, using the Viterbi decoder, the system determines the optimal, phoneme sequence that best explains the observed speech signal. Again, this same model that we have seen earlier, we have this input. From the input we have extracted the spectrograms. These spectrograms also we have said it is the 39 MFCC features. Now we have the acoustic modeling, where we are modeling the acoustic properties the audio features hold. And also we have the language model. So basically for the acoustic modeling we will use the Gaussian mixture model, and for the language model we will be using the hidden Markov model. So we have this acoustic model. So as we have already seen, for the every particular word, we have some the acoustic properties. So that can be presented using the hidden Markov model. So in hidden Markov model, the arrows integrates the transitions from one phonemes to the other. That is represented by the arrows. And the observed audio features are modeled using the Gaussian mixture model, which is the learned from the training data. So basically for the language modeling we use the hidden Markov model, and for the audio features we use the Gaussian mixture model. So, as the hidden Markov model, as we are already aware that the Markov chain presents all the possible states of the systems along with the properties or transitions from one state to another. So, over here you can see we have these three states, and the transitions from one state to the another states have some the weighted values. So, these weighted values, they are represented in the transition matrix. Now over here you can see we have these probabilistic scores of the each of the say of the Markov chain, where we take the word sequences, and we are taking their probabilistic scores value. So the first order Markov chain assumes the next state of the system depends only on its current states, which makes the model easier to work with. So it will only consider, or it will only be dependent on the current state whenever we are using the first order Markov chain. So in a many machine learning applications, however, the true states of the systems not directly observable. These are referred to as like the hidden states or the latent states. For example, the person's emotional state, like the happy state or the sad states, can be observed directly by using the this HMM property. Now instead we infer it from the say the observable actions we have. So if a person says a happy, we will say they must watch a movie with some probability. Also, if the person is sad, then there is a high likely chances that it will watch a movie. So it has the more probabilistic value compared to the say whenever the happy mood is there. So in this context, the probability of observing an outcomes given the hidden state is a emission probability. So the probability of observing a given say observing an outcome from the given state is called as the emission probability. Also corresponding to that, the equations we will see. Now, while the probability of moving from one hidden state to another hidden state is called as the transition probability. So over here you can see in speech recognitions we have the observable data that corresponds to the information contained in each audio frames, which is commonly represented using the MFCC features. Now using these features we can model the speech with the hidden Markov model. So over here you can see we have this chain. Over here you can see there we have the state transitions, where the from one state we are leading towards the next state. So that is our transition probability. And whenever we are observing from the any hidden state to the say the transitions that it has, that will be our the emission probability or the. So now with the help of our say the transition probability and the emission probability, we can build our the hidden Markov model. Now once the hidden Markov models is trained with all the informations that we have, so the we can also use the forward algorithm. So from say from going from a one state to the another hidden state, for that also we have this forward algorithm that can be computed. Also the forward algorithms, we will also compute the likelihood of the most observed say observed feature sequence. So the say the observed feature sequence which has the say the highest probabilities or leading towards the say the closer properties that can be leading towards the answers, so that can be used. So also this is done by summing all the probabilities observations that the hidden sequences has, allowing us to efficiently evaluate how well the say the model explains the observed speech signal. So over here you can see we have the probability of the all the observed events, where we have this emission probability and the transition probability. So transition probability is represented by all the say the state transitions we have, and the emission probabilities for the particular say the from the particular hidden state what are the observed sequences we have, that will lead towards the emission property. So summations of all these properties will be leading towards the final outcome. So we must compute this efficiently, since summing over say all possible state sequences directly would result in the exponential complexity. To address this, hidden Markov models uses the divide and conquer rule. So to deal with, since the whenever we have these scenario also in the speech recognitions, there will be like these will be like long videos. So for that the complexity will increase exponentially. So for that cases we have this hidden Markov models. We also uses the divide and conquer property, where the recursive competitions is taken. So the iterative also as well as the recursive competitions is taken to identify what exactly being said so that the complexity can be reduced. So by expressing the likelihood at a time t in terms of the results from t minus 1 to t plus 1, the problems is broken to the say manageable steps, although the number of the possible state sequences grows exponentially over the time. And this recursive information allows the computation to be performed in a linear time with respect to the sequence of the length. So this is the idea of the dynamic programmings where we uses the both the forward say forward algorithms as well as the backward algorithm. So with the help of these, there is a better chance of the having the say the greater accuracy. Also, in this case scenario, we will also see the sequences which might not be seen by the simplest Markov chain or the first order Markov chain. So we denote the highlighted terms with the alpha t that represents our forward probability. Examine whether it can be, say, defined recursively, since the current observation depends only on the current state, and the forward probability can be expressed in the, say, the recursive form. So this is the same scenario that we have seen. So we have the transition probabilities, we have the emission probabilities. At this case, you can see we have this extra terminology that is our forward algorithms that we have seen that can also be used. So whenever we are using the recursions or a recursively looking for the transitions within the observations we have, with the help of that, we can also leads to the better computational complexity that was not taken previously when we are only considering the transition probability or the emission probability. So at this case, you can see we have taken the transition probability, emission probability, as well as we have taken the forward probability, where the probability of all previous observations give at the last state I. Summing all these informations that lead to are the better outcomes or the better observations sequence that we will have. So here is an examples which we start with the initial state distributions on the left, and we will propagate the value of the a to the right, and we compute a for the every state and repeat it for the every time step we have. So over here you can see the two states we had is the happy state and the sad state, and corresponding to that we had the probabilistic scores. Also how likely the chance we have, so whenever we are in the happy state, how likely the chance that we will watch a movie or we will read a book or we will go for a party or for a dining. So these are the probabilistic scores. Also you can see the sum of these all these values at the say the rows will leading towards the one, since they are the probabilistic score. So also same case for the same case for scenario for the SAT. So also you can see with the help of these conditional probabilistic scores, the say the values that it holds, we can also generate how likely the outcomes of the of the persons being going for the movie or going for the party. Now, once a hidden Markov model is defined, the next task is to determine the most likely hidden state sequences given a sequence of the observation. So this process is known as a decoding and is especially important in a speech recognition. So in the context of the speech recognition, the observations come from an audio signal, while the hidden states corresponding to the phonemes that we have already discussed earlier. Therefore, the speech recognitions can be viewed as the problem of identifying the most likely phoneme sequence that explains the observed audio features. So now decoding, find the internal states using the Viterbi algorithm. So as before, we aim to use the recursive formulations that we have seen, the joint probability of the observation sequence and the most likely state sequence ending at the state J. So the state J we have started from the state I and we are leading towards the state J. Now, not only is this problem, but the resulting equation closely resembles the forward algorithm. So, in the say, while the forward algorithm consider all the possible state sequences by summing the probabilities, as we have seen that we have the transition probability, emission probability, and also we have the forward probability. So that will lead towards the more optimal path or most likely state sequence. Same scenario over here you can see for whenever we are using the forward say algorithms that lead towards the better say outcome. Now finding the internal states that maximizes the likelihood of the observation is similar to the likelihood method that we have seen. So we replace the summation with the maximum function. So in the previous cases, we have seen that we were actually summing up the all the probability of the say the transition probability, emission probability, as well as we were summing the say the forward probability. But in this scenarios, we will take the maximum of these. probability. So whatever the outcomes we have at the end, we will take the maximum value. So say in this case we will be using the maximum function. So in this algorithms we will also keep the track of the most likely path leading to each state at a time t by storing the back pointer. This allows us to backtrace the optimal state sequence, so once decoding is complete. For example, the model may has the transition from the happy state or the being at the same state. Now the next challenging is learning the parameters of the hidden Markov model. This is achieved by using the so this is achieved by using the Baum-Welch algorithm. So it is a say for the improving the learning parameters that we have. We also have this Baum-Welch algorithms which uses both. It uses the forward algorithms. It also uses the backward algorithms. It also uses transition and the emission probabilities. So it also, however, deal with the state occupation probabilities at each times. Say time steps, the transition of the emission or the say transition probabilities can be computed. Also conversely, if these probabilities are known, the state occupation probabilities can be determined. So the interdependence forms of the classical, like the chicken egg problems, which come first, like a chicken come first or the egg come first, these kind of the interdependence forms can also be leading towards the same. So to solve these problems, we have this expectation maximization algorithms, which resolves this by using the iterative process. It uses the say the recursion process as well as the iterative process, and it also we can say it uses the say local maxima or local minima properties. With the help of that, we can identify what the possible outcomes we have. Also, in this case, the algorithm with the help of this, we also lead towards the gradually converges the solution to a one particular peak value. So corresponding to that, we have the notations. So for the notations for the forward probability, we have is it represented by the alpha, which has the given at the time t with the internal state I, the probability of seeing all the observations we have so far. For the backward probability from given at the state time t with the internal state I, the probability of seeing all the coming observations. So backtracking all the observations that we have, so that is represented by the b beta. Then we have the gamma, which is the probability at a given state I at the time t given the observations we have. Then we have psi. So she probability of the transition from state I to J. So previously we were only focusing on the say the from the one particular state or being at the one particular state. But with the help of the say the Psi formula, we can also have the transition say probabilities of the transitions from the state I to the state J given the time we had. So we are already familiar with the forward probability that we have discussed earlier, also the backward probability which defines the reverse directions. So the say the backward probabilities is almost the same as the forward probability, only that the in the backtracking we start from the last hidden layer we have. Now likely the forward the probability it is represented by the alpha, the backward probability it is represented by beta. We also learn the hidden Markov model, say also using the expectation maximizations will be which will help greatly to identify the peak values by using the by using the bell curve or the Gaussian values that we had. Now the representations for that is mentioned at this particular slide. Now when the hidden Markov models are fixed, the forward and backward algorithms are used to compute. So whenever we have the fixed parameters, we use this say the forward or backward algorithms. That will also give us the say good results. But Psi is mostly used whenever we have the higher say variations in the output. Also with the help of this um, shy also we can also lead to the expectation maximization problems. Also we have the solutions which comes first, like the chicken egg problems can also be solved by the expectation maximization algorithm. Corresponding to that, also you can see we are summing up all the properties that we have seen. So previously we have seen the forward probability, backward probability, the say the strained occupation probabilities. All these are the sum up and leading towards the final outcome. Also, in the expectation maximizations, we are trying to optimize. So we are trying to learn the all the parameters we have, and we are trying to learn all the informations that we had and leading towards the better outcome. So we optimize it by learning all the values. So by going through the every possibility or every observations that we have identified within our audios, so we are able to reach to a conclusion. So with the help of say are the forward probability, backward probability, or say shy, then our gamma, all these will be leading towards the best sequence. Now the expectation maximization problems is shown in this slide. So we have the estimation step, then we have the maximization step. So all will be leading towards the final outcome. Okay, so using all the training observations by using the Bomb-Wedge algorithms can be applied to learn the hidden Markov models. However, it is important to note that the speech recognition is a much more complex problem, and in practice, some methods may not be scalable or efficient to large or a real-world data sets. Uh, so I will begin from this. I just need a 2 minutes break now. I'm just coming. So now coming back to the acoustic model. Okay, so these all sequences we have seen where we have taken the say the features. From the features we have used the say the classical signal processing. For handling the acoustic models, we have to go through the Gaussian mixture model. So we have currently only gone through the language models or the say the pronunciations models. How we can relate it with the help of the first we have gone through the hidden Markov model. Then we have seen the Viterbi algorithms, then we have lead to the say the forward probability or the backward probability, and then leading towards the say the expectation maximizations algorithms. So we can see that how we can say computationally solve this and also give the results in the say the feasible time. Now coming to the acoustic modeling. So in the automatic speech recognition, a pronunciation dictionary is used to convert a text sequence. It corresponds to the corresponding phoneme sequence, or the acoustic model is then built to represent these phonemes. So with the help of the acoustic model, we can use this to build our representations for the phonemes. So over the several decades, extensive research has been done on the phonetics, and it has shown that trained experts can directly identify the vowels, constants by analyzing the speech spectrograms. So with the help of these spectrograms, we can identify the vowels, constants. We can also able to identify, since the vowels, they usually have the, say, the high attribute values, and they has the high amplitudes. They also corresponds to the high intensity in the sound, so they can be easily identified also in the spectrograms. So over here we have this wide band of the spectrograms for the vowels of the American English. So you can see over here the intensity of the vowels is much. So corresponding to that, we can also able to identify. So however, there are the certain phonemes also which you say can't be easily identified in the spectrograms also. However, these spectrograms always play a major role in the, say, the phonetic representations also, since it holds the properties of the one particular sound. So that is also say the major thing that need to be taken. So we can also to identify the patterns of the phonemes, we lead towards the spectrograms. Now to say accurately compute the likelihood, say the for the particular phonemes, what the acoustics features that we have, the that can be used. So the acoustic model must use a dense representation of these speech features. So using MFCC, each audio frames is typically represented by the 39 features that we have seen. Now for simplicity, considers a reduced case where the each frames has only a one feature. So, say only instead of a 39 features, we are only considering the one features we have. So, for a phoneme, such as say SH, the values, so the phonemes SH is called as the sh. The values of these features can be modeled using the Gaussian normal distribution. So, over here you can see for the one particular phoneme, the this is our probability density functions that is mostly used in the, say, in the electrical engineering. So these probability density functions or the values leads towards the uh, value over here. So you can see these all the frequency that this particular phonemes holds will be stored over here. So with the help of these PDF, we can also identify it. Now to extend this idea to the 39 features, so we use the multivariate Gaussian distribution. So the previously we have seen the PDF, now we are using the Gaussian multivariate Gaussian distributions, where we have the 39 variables. So instead of a two variables that we have discussed earlier, now we are taking the 39 variables. So the diagrams below illustrate the concepts using the bipartite normal distribution, which represents the case of the two variables. So you can see if we are having actually the, say, more number of the features, and we have this Gaussian distributions values, so to identify what is being said, it is a bit challenging. So also we have to take care of the parameters. So say we can say the phonetic informations of the particular, say, the audio holds, that can be identified by using the Gaussian distributions. Now where the in the previous slide we have this summations, which is the covariance matrix that we have already say gone through whenever we have seen are the machine learning models, now which measures the correlation among the variables. As we are already aware that the covariance matrix, it holds the properties where we are able to identify or correlate two variables. So MFCC parameters have a very nice properties, they are relatively independent of each other. So uh, that is one of the say the major advantage that the MSCC features has, that it is say the features, they are the independent of each other. So with the help of the MSCC features, we can actually distinguish between the say between the audio samples. Also, therefore, the non-diagonal element of the sigma can simply let set to the zero, that we have also learned previously. Now it is a two hard to think multidimensionally, so we will stick with the 1D examples for the illustrations. The likelihood, as we have already seen, we have the pxq of the observed sequence, where the x will be calculated as far as it is from the peak, and the q will be are the normal distributions. Over here we have this formula. This formula is actually our probability density functions formula. So over here you can see we have this um, uh, uh, the standard deviations. Also we have to take the mean values, so corresponding to that we will be able to actually find the probability density function. So, corresponding to that, you can see, as we are already aware what exactly the mean is, what exactly the standard deviations is. So, by putting the values of these, we will actually able to have our acoustic models. Also, you can see in this particular slide, you can see we also take the differential equations. So, since also in the Gaussian's say distributions, we as we already aware that it is also take care of the local minima or local maxima. So it holds the property. Also we have to identify the differentiations of the equation. Now the Gaussian models is easy to learn from training data and provides a likelihood functions that is represented by the x divided by mu, and then we have the standard deviation square. So such as the Gaussian parameters can be learned from each phoneme used as the likelihood models, which also serves as the emission property as in a hidden Markov model. So however, even with the multivariate Gaussian mixture model, this approach is oversimplistic. However, these speech signals are far more complex than the single bell-shaped curve can represent. So, if a speech were this simple, learning new spokens would much be easier. So, in reality, the likelihood distributions is often multimodal, reflecting variations in pronunciations or accent or the speaking style. So, it is a bit challenging whenever we are dealing with the different accents, different speaking styles. Also, in this case, the complexity increases. So whenever since in this particular case we have only considered the one single features, but whenever we have like the whole when we building the whole say the model, where we'll be having like a thousands of the word categories, or the or samples will vary from the like the from the GBs to the TBs. In that it is a way more challenging. So to capture this complexity, we use the Gaussian mixture model. So Gaussian mixture model represents the distribution as the weighted combinations of the multiple Gaussian components, allowing the features to take a several probable values. And this added flexibility makes the Gaussian mixture models well suited for the modeling a speech variability. For example, the three compound Gaussian mixture models combines three Gaussian distributions with the different weights values to form a single the probability density functions. Although more expressive, the model remains compact, requiring only the six Gaussian parameters and the three mixture weights value. Okay, so intuitively, the feature values for the given say phoneme tend to form a cluster around. So, with the help of these clusters, or with the help of the features which has the say properties closer to each others, will be say closer in this. We usually form the cluster like of a structure. So whenever the hidden Markov model state is a j, the likelihood of the observed feature vector is computed as the weighted combinations of these Gaussian components. Now, to train a Gaussian mixture model, consider a simple case of the two components. So, feature vectors extracted from the training data are used to estimate the parameters of a two clusters. The process begins with the initial parameter estimate, and each data samples is then assigned to the most likely clusters, which often lead to what exactly being said. Now, same we have this expectation maximization algorithms, which is iteratively used to refine the Gaussian mixture parameters. So, by using the all the informations that we have, we use the local minima, local maxima, to also the differential equations in the Gaussian mixture models that leads towards are the better likelihood sequence that we have in the observations. Now, the model parameters are then updated using on these probabilistic assignments we have. So, in summary, for each phoneme, the Gaussian mixture model is say used to model the distributions of the observed feature vectors, and this distribution enables the computation of the likelihood of the from the say the emission probabilities of the corresponding hidden states in the hidden Markov model that we have seen. Now the vector quantization. So instead of using the Gaussian mixture or acoustic models, the other properties we have is the vector quantizations also. So where we usually use the say the feature vectors, and we generates the clusters values. Now coming to exactly the fusion approach, how, since we have now gathered how we can say gather the informations from the lexicons, how we can gather the informations from the acoustics, how can we gather the informations from the language. So by fusing all these together, we can lead to the better accuracy. So the also in the say that whenever we are generating a model, for example, so, let's suppose we have this video samples. So in the video samples we have this audio as well as we have the images. Now these images, this the whole video can be broken down to the frames. Now and all these properties or the all these informations gathered from the one particular video can be fused together, and with the help of these say the input informations that we have, we can have the better accuracy. So that is one of the key advantage of learning the multimodal fusion. So what exactly the fusion is? The fusion refers to the process of combining information from multiple resources. So we gather the information from the multiple sources, like we gather the information from the sensors, we gather the information from the image, we gather the information from the camera. So these are all the multiple sources from which we can gather the informations, and then we will lead towards the more accurate or the reliable or the meaningful decisions that any single source can have. Okay, with the say in the only the single source, the say the accuracy or the result won't be the say the good. But if we combine the informations from the various sources, then the say the output that we had will be say the more accurate, it will be more reliable, and it will make a more say meaningful decision. So, in the machine learning and the artificial intelligence, the fusion is especially important when a problem involves different types of the data or the features. For examples, we have the audio, text, images, sensor signals. Now, think of a fusion like the human perception, like the human see, hear, or the human say predict. So, all these informations that the human takes, and with the help of that, it will identify. For example, when we understand a speech, we don't really rely on the sound only, we also sometimes see the lip movement, we also try to identify the context, try to find the intent and the meaning. So fusion inmates this idea is in the computational systems. So fusion inmates this idea in computational systems. Now fusion in artificial intelligence and machine learning. So fusion typically combines the multiple modalities we have, like audio, visual, and text. Then the multi-feature feature sets, as we have seen, we have this mel frequency, substrate coefficient, the spectrograms, and the embeddings. Then we have the multiple models or the classifiers. So the classifiers that we have seen, like the Gaussian mixture model, the hidden Markov model. Also, we have the classifiers like the Balestier models, LSTM model, recurrent neural networks, or we can say we have deep neural networks. So all these models, we also have the support vector machines. So these all can work as the classifiers. The audio features we have is the captures the acoustic patterns, the visual features they captures the lip movement, and the linguistic features they captures the phonemes or the language structure. So fusion combines all these three to improve the say recognitions or the accuracy. Now, the multimodal fusion case study, device directed speech detection, which is also called as DDSD, it is a binary classification problem that aims to differentiate between the speech intended for the voice assistant and speech arising from the background conversations or the ambient audio. So, it takes the both, it takes the voice assistants or the what is being said, and it also takes the background conversations or the ambient audio. So this capability enables the voice assistants to recognize when users intentionally issues the commands, which greatly helps whenever say the commands based systems. So whenever it generates the commands, with the help of that we can know what is the most important informations to gather, the device would know. So the DDSD is inherently challenging because a voice assistant must reliably disseparate users' commands from the competing acoustic conditions. So the background noises or the ambient sounds that has been playing around the audio can be removed, so including the loud background noises. So with the help of these binary classification problems, it is able to identify which information to gather and which information to lose. So it will lose all the, say, the noises from the background, and it will only take the informations where the command is being said, and corresponding to the command, whatever the sequence of the sentence that being said by the speaker, it will take that. Now, to improve the robustness and the accuracy of the triggered word detection systems, like multimodal fusion approaches can be employed that integrates both the verbal and the non-verbal cues. So, verbal cues capture what is spoken, while non-verbal cues say provide the complementary informations about how the speech is delivered. So these non-verbal signals include the prosodic characteristics such as the pitch, the intonation, the stress, the rhythm, the intensity. So all these represent the prosodic characteristics of the sound. That is also can be called as the visual cues when available. So, for instance, when addressing a, say, voice assistance, users typically speak more loudly or slowly, articulate the words more clearly, and avoid the hesitations or the fillers like uh. So whenever we are addressing any voice assistance, the users typically speak more loudly or slowly. So also to differentiate between the sound and the say the verbal cues and the non-verbal cues. So these they are the non-verbal cues. So while the traditional acoustic based the DDSD systems primarily focuses on the lexical content, the prosody aware where we have the pitch, the notation, the stress, the rhythms, the see the DDSD will take care of that, and it will take that as the more important information to which will lead towards the more accurate say answers whether the utterance is a device directed. So combining these different modalities of the informations, we are enable the model to utilize the verbal inputs as well as the salient features of the non-verbal cues, so leading towards the enhanced triggered word detection. So the strategies for fusions we have, so multimodal say models can gain the significant performance improvements by integrating the information from the multiple modalities. However, the effectiveness of such systems strongly depends on how and at what stage this fusion is carried out. So understanding the embeddings. So in these, say, the different modalities we have, like the text or the images that can be transformed into the shared representational space, which is called as the embedding. Now the embeddings is a more like a compact and the machine interpretable numerical vector that encodes the most salient semantic informations from the original input. So it maps the informations of the say the maps the informations like the from the text or the images represented into some the vectorization forms. This whole representations lead towards the numerical vectors that are say the embedded together, and that will lead towards the more like a semantic or the meaningful information. Now, by mapping the diverse modalities into this common embedding space, the models are able to say identify the reasons about them to at the same sentence semantic level. For instance, an image depicting a cat wearing a sunglasses can be represented by the 16-dimensional embeddings also. So while the sentence "this cat is wearing a sunglasses" can be decoded into the embedding of the same dimensionality. So whenever we have the informations from the one single say the image, we have the two forms of the input. We have the one input as the image and the other input as the text. So the both these are represented in their vector form. Now after vectorizations we are embedding these together, dimensionality is taking the summations of these embeddings together. So comparing these embeddings allows the model to infer the semantic similarity between the visual and the text representation despite their different formats. So from the audio, we usually have the audio models. So we model for these audio models, we vectorize the model by using the vectorization techniques that we have. So we have the those embeddings of the audio called as the audio vector embeddings. Then same for the text. For the text, we have the text models. Now the from the text models, for examples, we have the models like the face to text model, The other models is like the fast to text, the suffered modeling. These are the some of the say the text models that we have. Also, we have heard about like the glove embeddings, which is the most likely used whenever we are generating the vectors for the text. For the audio, we have already earlier seen like the MSCC features or the mel spectrogram features. So these representations can also be used as the embeddings for the audio. Now for the video scenarios also, we have some the video vectors representations by using the certain computer vision models. We can also vectorize the video. So all these vectorizations and the embedding techniques or the informations from these sources can be gathered and fused, so that will be leading towards the best accuracies or the best results. So fusion of the multiple modalities. So multimodal fusions is a commonly implemented using the four general strategies we have. So which differ primarily in the stage of the model pipeline at which information from different modalities is combined. So it totally depends upon the how the information is gathered. Based on that, we have the four types of the fusion techniques. The first fusion technique we have is the early fusion. So modalities are merged at the input level to form a single unified representation, so which is then fed to the learning model. So you can see in the early fusions we fuse the input, say the inputs that we have, we fuse it before giving the input to the learning model, so that say the fusion property is called as the early fusions, where we have taken the input and the fused the inputs together and then given it to the learning model. At the intermediate fusion, each modality is first processed independently, and then to obtain the latent representations, once we acquire the latent informations, then that can be fused or jointly learned. So instead of giving the say the performing the fusions at the earlier stage, it was performed a little intermediate stage. It performed a little later stage. For the say the late fusion, the each modality is handled by the separate model. So the whole model, say the models is trained on a different models, and later on the say the results that we got, that will be fused together. So that will be leading towards the confidence scores, that will be leading towards a decision level scores. So those scores when later be fused together after like a learn after training the models to the two separate or more separate models and then fusing at the later stage. Now the hybrid fusion, the combinations of any fusion techniques that we have seen like early intermediate fusion or the intermediate late fusions or the late or the early fusions, that can be lead towards the hybrid fusion. So the fundamental distinctions among these three approaches lies not only in what is a fuse but in when the informations need to be fused during the modeling process. Now discussing the each fusion techniques in a detail. So first we are discussing the early fusion technique. The primary advantage of this approach is that it eliminates the need of for the separate processing pipeline for each modalities. All modalities are combined directly at the input level, and the resulting unified representation is a passed through a single model. So in this case, you can see we are fusing the input together. So the informations that we acquire at the inputs, they are fused together. That is the main lead towards the early fusions. Before giving the say the information to the say the classifiers, first we have the fusions at the earlier input stage. Now this strategy is particularly suitable when working with the multiple sources of the same modality. For instance, in the sentiment analysis task on like Amazon book reviews, a model may leverage not only a review text but also complementary metadata such as the price, the author information on the genre. So it extract the information from these the various sources, and after these informations, they are combined, and then it will be later given to a classifier to identify. Now, these simple text concatenations can effectively integrate these inputs into the single representations, which is then fed into the sentiment classification model. However, key limitations of this method is that the raw input representations often lack the rich semantic structure. So, as a result, the model may struggle to learn complex cross model interactions, thereby constraining the overall gains achievable through the multimodal fusion. Then we have the another fusion techniques. The second fusion techniques is the intermediate fusion techniques. So the intermediate fusion techniques is the most commonly adopted multimodal fusion strategies. In this approach, each modality is a first processed independently. So, well, first the modalities will be say the processed independently to obtain some the latent representations value or the embedded representations value. Then they will be fused together. So the latent representations then fused, followed by the additional joint processings to generate the final outcome of the prediction scores value. Now, at this case, you can see it is not fused at the early stage. It was fused in the later on stage, and also after acquiring the latent representations. Processing the modality separately, then we say fused it, also we pass it to the joint processing modeling, and then keep repeating that. So a particular example for the intermediate fusions can be found in the autonomous driving systems, where the information from the heterogeneous sensors such as cameras, lidar, radar, gps must be integrated. So, because these modalities differ significantly in structure and scale, they can't be combined directly to the input level. As in the early stage instant, each sensor, say, streams is transformed into the latent representations, which is subsequently fused and jointly analyzed to determine the vehicle's next action. The fusion of the latent representations can be implemented in several ways, including like the vector concatenation, the element-wise additions, and the attention based mechanisms depending upon the model design. So the key advantage of the intermediate fusions is that it enables the model to learn the rich and the meaningful interactions across the modalities, since each modalities is a first mapped into the machine interpretable representations. However, this approach requires the separate processing pipelines from the each modality prior to the fusion. So, although the availability of the pre-trained, say, embeddings for the modalities such as the text, images, audios helps mitigate this issue, and the additional, say, processing can still affect the say, inference latency and overall system efficiency. Now, the third fusion technique that we have is the late fusion. So, late fusion closely resembles an ensemble-based approach. So, in this approach, each modality is processed independently using its own dedicated model. So, each say modality will have its own say independent models. So, then at the later stage, once it identifies the results or it classifies the models, then their predicted score values can be combined. So that is what exactly the late fusion is. Now, a representative example of the late fusion is the genre classifications from the say the YouTube videos. Given the video link, one model may analyze the visual content of the video to predict its genre. Same way, a separate model we have for the video transcript description to generate the another genre prediction. Now, after acquiring these predictions, later it will be fused together. So that will be leading towards our late fusion. Now, these independent predictions can then be aggregated using the techniques like we can also use the say the weighted averaging, where we take the say we have the some the with the probabilistic scores, we have some the weighted values assigned, and also we can use the say the summation values. Also we can combine all the informations we have from the two different say independent predictions and takes the maximum value among those two predictions. That can also be used. So these are the few techniques of the latent fusion, where we have is the weighted averaging and we have the see the summation approach. Now the primary advantage of the late fusions, it is a simple and it is a modularity, since it has the say the independent predictions. So also it is a bit way simple compared to the intermediate fusion technique that we have seen. So each model can focus on learning highly detailed informations and modality specific representations without inference from the other modalities. However, a key limitations of this approach is that it fails to capture the complex cross-model interactions, preventing the models from the directly exploiting the complementary relationships that may exist from the different modalities. Now over here you can see we have the examples for the early fusion. So at the early fusions you can see we have acquired the information from the say the bag of the words, the bag of the 2 grams, the bag of the 3 grams. Then we have LDA, UMLS and the wordnet. So we have these say informations gathered from the various the techniques that we have. Now after these informations we combine these values together. So that will be leading towards the say the early fusion technique. and then later passing it on to the to our classifier, that is the support vector machines in this case. So this is an example for the early fusions where we say fuse the all the input informations that we have together before giving it to the classifier. For the same examples you can see for the each say features, for the each features we have given it to the classifiers might predicted something. Now after acquiring the say the probabilistic scores of each of the models or the predicted scores from the svm model, so you can see later it will be say the we will use the approach like the summing the scores values that we have, or we can take the maximum values. We can also use the weighted averaging values. Okay, so based on that we will predict what exactly been the output. So over here you can see we have this earlier fusion techniques. The representation over here you can see we have this input value. So the at the early fusions we usually fuse the say the input together. However, in the intermediate fusion technique you can see we have this input value. Now they are represented in some latent representations and then given it to the model. Also you can see it is coming back. Also you can see we have the representations from the other case also. See over here you can see we have the neural network. We have the from the input after the neural network we have some latent representations which is given with the input. That was not the case in the earlier fusion technique. Now for the late fusion technique you can see we have the input, we have the say the separate inputs, separate models. Now the after acquiring or classifying the first model and the second model, later they will be fused together. So the whatever the predicted scores we will have, the predicted scores will be fused based on the decision approach that will be used. We can use the weighted average property, we can use the summation, we can also use the maximization. So whatever the see the functions we can use uh, to identify what is being predicted. Now the modality dropout, the data scarcity at inference. So multimodals are powerful because they integrate the information from the multiple sources. They develop a more comprehensive understanding of the task. However, training a machine learning a system on a multiple modalities typically assumes that all modalities will be available during the inference. So an assumptions that may not always hold in the real world scenario. So ideally, a robust system should be capable of leveraging all the available modalities we have while maintaining the reliable performance when we have the one or more modalities missing. So one effective approach is to address this challenging in the modality dropout. So this technique involves randomly omitting or masking the certain modalities during the training by encountering the model to learn under the varying modality combination. So with the help of this we can also able to improve whenever we have the data scarce where the we don't have like the much informations as the input. Also as the result the model becomes like a more adaptable and can make the reasonable predictions using the say the whichever the modalities or the whichever the information set can. So some of the my observations in my PhD I can show you. So over here you can see, well, I have worked on the one of the say the famous data set, that is the Google speech command data set. So in that we had like a 10 word categories as well as we have the 35 word categories. So at this particular case we have the various categories like the or the words that being said by the different speakers, like yes, no, up, down. So these are the some commands, sort of the instructions that we have. So they are represented in the say the 10 word categories. For the same data sets we also have the other categories like 0, 1, 2, 3, 4, 5. So these are the certain other words that is also being said. So this is the see the data set that is been say developed by the Google. So they have called it like the speech commands, and it the one of the papers related to it is the given in by the Pete Warden, where it has the speech commands a data set for the limited vocabulary speech recognition. So in this particular data set it is a basically we have the different speakers. The different speakers might have spoken the words with the different say articulations. Also the intensity have varied. Also these say the data sets, it has the say the it is of the 1.25 GBs. So it was a huge to process these, since each of the audios also requiring like a lot of the storage to identify it. Well, the model that I have used mentioned later on. So you can see the this is the same chart that we have seen, that is the international phonetic alphabet. They have represented it. So they have represented the phonetic chart. So with the help of these phonetic information, we can also identify what is being spoken. Now over here you can see, well, for the one particular word like a backword, I've taken the word like the backword. In this case, you can see first we have this phonemes. So over here you can see I have taken the phoneme sequence, where you have can see the we have the various stress levels, like the one that represents the stress level, then zero represents no stress. So these are the phonetic representations that is taken from the same international phonetic chart that we have. Also you can see these are the representations of the phonemes that we hold in the IPA. In this particular IPA, since the information that it has, well, the information that it takes totally dependent upon the grapheme that we will send. So whatever the word we will give to the phoneme sets, with the help of the say the best suited sequence that a particular letter will have, the corresponding to that the phoneme will be generated. So for that we have this grapheme to phoneme model. Now coming to the approach that is being used, so over here you can see we have taken the same data sets that I have discussed, that is the Google speech command data set. Now the to improve the audio quality of the audio samples, I have used the median filtering techniques. So this is the one of the most common filtering techniques that is used. Also say the results from the various other filtering techniques has been firstly observed, but it has been I have through my studies I have identified that the median filters usually result to the better say resultant values or the better accuracy. So you can see these after acquiring or after converting the say audio samples to the say the enhanced speech samples to the they say the filtered samples, then I have extracted the mel spectrograms. So you can see from speech, I have generated the mel spectrograms. The each mel spectrograms is of the 256 cross 256 in size, since they are the say the 2D representations of the say audio waveform. And all that you can in this particular waveform you can see are the say the y-axis we have the frequency levels, and at the say the x we have all the time steps. Now, these information, the informations that I acquired from this audio waveform represented in the 2D representations in the MEL spectrograms is further given to the Swin transformer. So over here you can see this Swin transformers has the various layers. So it has the like a patching, merging, linear embedding. So these are all these Swin transformers layers or all the informations that it acquires from the MEL spectrograms. And this Swin transformers, it is say the already been trained on the 14 million ImageNet data set that it has. On those annotated images, the say this is Swin transformers has been say one of the computer vision models that is used majorly for the image classification. So I have used the image classification of the spectrograms, which I have taken as the input for this particular case. Now you can see another, I have taken the independently the different approach, where we are from the same say Google speech command data sets I have extracted the text. Now from this you can see I've taken the sample as a where I have taken the audio sample as a down. So I have converted this speech to the text, so I got the letters, the characters of the word down. Now after this I have separated the say the suprasegmental details and the non suprasegmental details. So with suprasegmental details we usually have all the stress levels or the say the within the phonetic informations we also takes their stress levels as a 0 1 2 representations as well. So in the say the without suprasegmental details we have all the informations where the say the stress levels are missing. Now after acquiring their phonetic representations in these two say details like a suprasegmental details and non suprasegmental details, I further use the phoneme slicing. So you can see at the phoneme slicings we use the the say the that I've seen in the shown you in the IPA chart, where I have taken the vowels and the plosives. So mostly, why I have taken the vowels in every possible case is that the vowels usually gives the, say, the higher amplitude and also has the high intensity. So to identify a particular word or the particular phoneme with the, say, the vowels will make the more say will lead towards the better result. So with every, say, the place of the articulation, I have taken the vowels as well. So now I have taken the vowels and the plosive. So majorly the examples for the plosive we have is the B, D, J, P, T, K. So these are also called as the stop consonants. Since while generating these sound patterns, they we have the stop airflow. So combining that informations, also we have the, I have taken the vowels plus fricatives, where the with the vowels like a, e, I, o, u, I have also considered the fricatives like the say the f, s, v, z, which gives the hissing sound. Also I have taken the glides, the lateral fricatives, that all the informations that is already been given at the international phonetic chart. So I have just separated the informations which I really want to identify what kind of the results we get when we use the other say the places or the manner of the articulation the sound is formed. So after gathering or slicing all the phonemes informations that I had, further I have performed the phoneme embeddings. Now the over here you can see I have used the two phoneme embedding techniques. The first one is the universal sentence embedding techniques. The another one I have used the sentence but embeddings. So both of these embeddings, they are the generated by the, say, the Google. However, it is been say the sentence to say but embeddings techniques. It has been improved by Rihanna. So now after acquiring the embedding techniques in the, say, the two different forms, I have given all these informations which I have gathered from this, all the embedding techniques that I have gathered, and further I have given it to the to my classifier. So basically for this approach I have used the Balestier model. So now this is all these informations acquired from these different properties from these different sources. I have given it to the classifier. Now after the classifiers it will predict the value. So you can see, since the Google speech command datasets, it has like a 35 word category. So over here you can see the probabilistic scores values, or the say the classifications it occurs, it has the 35 word categories. Now after these I have say combined these probabilistic scores, or taken the average score value. So after this the resultant value will